Today I'm very happy and I'm very honored to have the opportunity come here. This is my first time to AIP. Also, this is the first time to Japan, to Tokyo. It's a lovely city and a lovely, nice people here. So thank you very much. I will talk about the recent work in my laboratory. The title is Multi-Modal Robust Speech Processing Analysis and Recognition is a Reality. Okay, this is outline. I will first introduce the background and describe four aspects of the speech processing with multimodal, and finally the conclusion. As we know, people do the communication is multimodal based. Several I list here: the verbal communication with language and paralanguage, and the written communication with message, book, blog, and the visual communication with image, video, and signs, and also some other non-verbal communications such as gesture, facial expressions, and such as that kind. So we wanted to develop a machine systems, also multi-modal based, just not the single model based. As we know, the speech and the language is the most important model for the communications. So we want to make the speech and the language as the and the core center, and in that basis, and add other models to make the interaction more efficient. There are many advantages for the multimodal speech processing, such as higher performance and better accuracy and more robustness. And my team focus on this topic for several years, and mainly focus on such tasks. For example, the speaker identifications, also person identifications with different features, and the speech separation and the enhancement with also multimodalities, and the speech recognition and scene analysis, and also the multimodal self-supervised learning as a large language model is also very important. But today I will mainly focus on the previous four tasks: the speaker ID, speaker separation, speech recognition, and scene analysis. Okay, the first one is multimodal speaker identification. Around 2000, several research is revealed that there's strong correlations between one's face and voices. And one of the face's many functions is that it comprises the out face of the vocal tract. So, based on this motivation, we think we can using the two modality more efficiently to make the systems better. So first, we want to do the person identification. As we know, the voice also is an important biometric features to identify the people. We can also use in some applications on our phones. I don't know whether in Japanese market whether have some applications with the voice identification, but in China, such as WeChat, you can using our voice to log in to the WeChat. We don't need to put our password. We just speak with one utterance and then log into the WeChat. Okay, but for the different modality, they have also their own limitations. Such for the visual, for the face verification. As we know, face verification is more popular and deployed everywhere. But they also have some limitations, such as wearing a mask on dim light, on low resolution, and such as kind of things. And for the voice, also, we know if you are in a noisy environment and the SNI is very low, even the people, the human beings, cannot listen clearly. How we make the machine to listen clearly? Okay, right? So the different modality have these different limitations. We do the observations on the famous multimodal data set that's Vox Celebrator collaborated by Oxford University, and the top part is the positive pair on two modality from the same people, and the bottom part is from the different people, but for the two modality. We can take the positive pairs, for example, their face are different clearly because such as wearing the different glasses and have the different color of hair. So they looks like different people. If we're using the face identification, it will make wrong decisions. But if we lessen the utterance from these two samples, they are from the same people. We can make the right decision. So from these observations, the facial and the voice information complete each other when doing person verification. So that's the motivation for our first work for the people identification. We constructed the neural nets. We know everything is neural net based one now. So we have two embedding extractors first. One is for speaker embedding, another is for facial embedding. One is for audio modality, another is for the visual modality. And then combined with a fusion network. Finally, you can use the person identification loss function to make the different modules trained jointly, and then you can deploy it for the normal person identification. Okay, so we just compare the result from the red blocks. We can see our system is much better than the single modality, and also much better than the traditional multi-modality-based systems. As I previously described, the different model, the different modality have the limitation. So we need to address if one modality is corrupted or missed, how can make the multi-modality system also perform well? Okay. First, we construct the noisy evaluation set. We make the data from one modality missing on corrupted with different types of corruptions, such as make some low resolution and cut part of the image, or make the noise, make the speech with different kind of noise or reverberations. The main idea to address this modality corruption is on the data augmentation, but different from the normal data augmentation method on the signal level. We make the data augmentation on the embedding level. For example, we construct the noisy data and the clean data on both modalities, and they pass forward a neural network to extract the embedding, the noisy embedding and clean embedding. Then we can use the noisy embedding to minus the clean embedding. We assume this new embedding is noise embedding. Okay, clean signal add noise is the noisy signal. We think so. The noisy signal minus the clean embedding is the noise embedding, and then we're using a Gaussian mixture model to model the distributions of the noise embedding. Okay, in the final data augmentation stage, we just generate the new noise embedding from our estimated distributions and add it to the clean embeddings. So finally, and then pour all this noise embedding with the original data's embedding and train the new model. It is okay. That's the two advantages for this data augmentation method. One is we can make the data augmentation more efficient because we don't need to do the data augmentation on the signal level. If you do it on the signal level, you need to store the new level and do the feature extraction on the new data. But we only do it on the fly and generate the embedding directly. Another advantage is that we can generate more diversity noisy data in reality, because you generate the new data embedding according to the estimated distribution, not the noise types. Okay, that's the result. We can see the last column is a new method. We can see the proposed data augmentation method can help the system learn more robust embedding, and the system embedded by the DNM method will perform well on the clean evaluation set. And the last one is a new data augmentation method generalize well to the unseen noise. Okay, and then I switch to the second part, multi-modal speech separation. As we know, speech separation is a very difficult problem in the speech processing. In this task, we want to separate the different sound source from the mixture sound. For example, 2 or 3 speaker or even more speaker speak simultaneously, and we can't hear clearly from this mixture. So we wanted to have the speech separation technologies to separate the signal from different speaker and make it hear clearly. Okay. In the real scenario, humans often utilize information from multiple modalities to assist these scenarios. For example, except for the audio, we can use the visual on the contextual to help you to understanding and extract the trace, the interested speech source. In our first work, we wanted to do the audio-visual speech separation with the attention mechanism. That's not a new idea from now, but it is a new idea around 2020. I think our work is the same work as Oxford, the work on the audio-visual speech separation in the same year. And compared to their work, we firstly add the attention mechanisms to do the 2 modality fusion. Okay, that's the result. We can see compared to the 1 vision stream on the Oxford, the 2 vision stream, our new system can get a consistent speech separation improvement. Moreover, we know people try to separate one's speech not only using audio and visual. We also using the contextual to help you to separate your interested speech. So we wanted to add contextual modalities. So how to extract the contextual modality is a key problem. We're using a knowledge distillation from a single talker speech recognition encoder to teach a multi-talker speech recognition encoder. This module can extract the contextual embedding from the mixture speech directly and accurately. If you are interested in the detail, you can look at the paper. And after the extraction, we plot the contextual embedding visually. We can see that here are the different words with the same circle. We can see the different speakers separate clearly, and the same words from the same speaker cluster in the same positions. So this new model can extract the context embedding from the mixture accurately. Finally, we can add this context embedding to the speech separation systems as normal. Just here with the embedding add, and to a separator, and to optimize with the separation loss function. We can see here from the result. Here we're using 3 different backbone with ResNet, DLSTEM, and TASNet. For different backbone, this new method add the contextual modality can get a consistent and a large improvement. Finally, we wanted to integrate all these 3 modalities, include the audio, visual, and contextual. So we named lesson, watch, and understanding in a cocktail party. And as normal, when we finish the embedding extractor and we concat all the embeddings from the different modality and to a separator and do the separation. Yes, here is the final result comparison. From the normal 2 modality to our 3 modality, we can still see a large improvement. Okay, here's an example for the speech separation.
A comprehensive plan to replace Obamacare.
Of course I have.
Well,
I got rid of the individual mandate.
I'm going to give you an opportunity.
I got rid of the individual mandate, which was a big chunk of
Obamacare.
That is absolutely a big thing. That was the worst part of Obamacare.
Sir,
Chris, that was the worst part of Obamacare.
Let me ask my question.
Well, I'll ask Joe.
A comprehensive plan to replace Obamacare. Well, I'll give you an opportunity. When I finish, I'm going to give you an opportunity. That is not a comprehensive plan. That I didn't ask him, sir. You're debating him, not me. Let me ask my question.
Yes, I have. Of course I have. I got rid of the individual mandate. Excuse me. I got rid of the individual mandate, which was a big chunk of Obamacare. That is absolutely a big thing. That was the worst part of Obamacare. Chris, that was the worst part of Obamacare. Well, I'll ask Joe.
Okay. That's a debate in last president election in America, and the debate between Trump and Wallace. So they speak simultaneously. If we listen to the original audio, we can't hear clearly for the 2 people. But using the speech separation, we can separate their speech and hear clearly. Okay. Okay. Then I switch to the multimodal speech recognition. Speech recognition is a popular and well-known task, but as we know, people do the speech understanding not only with speech, but also with the visual signal, mostly the lip motion. For example, if you listen, if you listen some people speaking, you look at you do the listening when you look at him on. Don't look at him. Your human beings, the recognition rate is also different, especially in a noisy environment. You can try. If you don't believe, you can try. Look at him to listen, and don't look at him to listen. Human beings' recognition rate is different. So that's because the visual signal is also very important to help you to understanding the speech communication. But these 2 modalities have their own advantages. The audios, as we know, it has the good intelligibility for the understanding, right? Most information is from the speech, from the language. But also the visual, the lip movement is also very important. It is noise invariant. For example, no matter it is noisy or clean, but if your camera is okay, the lip movement is okay. We'll make it the same. So we want to combine the different modality to make your speech recognition more better, especially in the noisy scenarios. Here are some general speech recognition systems for the 2 modalities. The basic architecture has just as these pictures. They have also two streams. One is for the audio, and another is for the visual, and do the combination, and then have the different loss functions to do the speech recognition optimization. The loss function is ASR based. Okay, in our work, but in the previous work, the traditional concatenation is frame level. It's just the visual stack with the speech frame by frame. But this concatenation suffers from the asynchronized issues of manual alignment. For example, if the visual and the speech have different frame rate, and one modality is delayed several frames, if you do the stack concatenation, they'll have the long alignment information for the backbone. Okay. So we propose a cross-modality attentions. Here, just we don't stack the two modality as normal, but we just concatenate from front and to back, and do the whole sequence with self-attention, so it can learn the alignment automatically. I will skip the detail due to the time. We can combine the result. Our new system is much better, both in clean and noisy scenarios. Okay, I will first switch to the last part, the multi-modal scene analysis. Okay, what is scene analysis? We normally know scene analysis using the visual modality. For example, we have many cameras and can do the scene analysis with the visual. But also audio is also very important modalities. If we have many microphone arrays, it can hear as a human and 24 hours, 1 day. So how can we do the scene analysis just with the on the audio modality? Also, you can use the other modality to assist this scene analysis. In this work, we want to do the target sound extraction with the modality clue. For example, in this complex scenario, we have some music, some speech, some air conditioned noise, and some reverberations. And the people wanted to, with some clues, and extract your interested audio source. For example, sometimes we are interested to speech, sometimes to music, sometimes to the air conditioning, the noise. Okay, I will skip this. And that's the normal architecture for the target sound extraction with a clue. Clues describe the interested event. And here the mixture of sound and the extraction model with the target loss function and optimized jointly. And in our work, our clues is a different model. You can use the text clue, the video clue on the tag clue, and concatenate together with this for the key and the value, and the original mixture is the query. Do the multi-clue attention, and then do the separation. Okay, let's listen demo. Here is the input audio. The input audio have two kind of noise, two kind of sound source. One is the baby cry, another is the typing keyboard. If your clue is this text description, a baby cry loudly, we can extract the crowd baby from the mixture. If the text is the sound of typing on a keyboard, we can hear the keyboard, typing keyboard. This is another example. One is speaking, and the ring, and the ring noise in the background. And the text clue is a man is speaking over a loudspeaker. This is the extracted sound. And the text is a telephone is ringing and ringing again. That's only the ringing. Okay, I will do the conclusion. Multi-modal plays an important role in robust speech processing, but there are still common issues to be tackled. Robustness to low-quality modalities on modality absence, efficient processing on a low-power edge device, and how to do the unified framework for different modalities. And another one is better cross-modal pre-training strategy. We want to make machines with human-like multi-modal processing capabilities, but there's still a long way to go. Okay, that's my talk. Thank you.
Okay, thank you for a great talk. So, any question?
Okay.
Compare with the voice sound, compare with the vision.
Yes.
What's your opinion? That what's the challenge in compare with the vision recognitions?
For the speech.
Yeah.
Okay. My opinion is that also visual is very important and challenging, I think.
Yeah, of course.
But different from the visual signal, the speech or on the audio signal.
Maybe the parameter of the space for representing the audio is much less than visual.
Yes, much less, but it is more random, I think.
Thank you.
Yeah, the variation may be larger than the visual, because for example, you can speak Japanese on SJTU many times, even speech at the same time, but the signal have the very different variations. But I think if you take the photo continuously, we can't clearly separate the difference between the consecutive photos. That's one feature for speech on audio.
For the security, you know, sometimes we recognize a face of the person.
Yeah.
And you see that you can also recognize a person by voice, but it's really robust or stable.
So
robust or security.
So I stated that
I can play a very high accuracy sound recorded by police.
So I think
and then the equipment catch the sound and can the equipment recognize which one is the real person or not?
we haven't that conclusion. So my suggestion is that we should make it multi-modal based, not single model based.
So you need still rely on some of the visual explanation, for example.
It's to the end.
Yeah.
2 minutes, 2 minutes earlier.
Understand what's your say.
Yeah.
Maybe we can discuss in the poster
You are
session.
happy or you
Yeah.
are point to some person else. So different cases.
Yeah, I think. Okay.
Yeah. Okay, thank you. So given the limited time, maybe you can discuss more in the poster session. Okay, let's welcome Wei Huang for his talk on.
Thanks again for waiting. So, okay, let's keep going on. So, yeah, so it's about like neuroactive learning. So let's introduce. So this is about like deep learning. So why deep learning is so popular? So everyone here maybe use deep learning because it is powerful. But sometimes deep learning does not work. So when? So because when sometimes the data is label is expensive and we need a lot of like efforts to label the data. So is any solution to this case? And our answer is like we use active learning. So what is active learning? It is about like instead of like labeling all the data, we just label a subset of or small amount of the data in our like data set. So here is a plot that's showing how active learning do. The first step we will try to select like most informative sample from the pool, data pool, and after that you can like put your labeled data to your like training data set, and you train your model based on this data set, and you keep going on like in this kind of loop, and after you train, then you like have more knowledge about your data, and you can try to sample like most informative data. So this is also a method that the human in the loop. So then if you are going to like apply active learning method, so which kind of like method are you going to use? So basically we have two primary like popular criteria to help you sample the data for active learning. The first one is called like uncertainty sampling. When you try to like estimate what kind of the data is most informative, you can like make use of the certainty. The method is try to find the most uncertain samples from your labeled data. Then after that, you can try to sample the data to ask the human to give the label to these most uncertain samples. And the second is about like diversity. So you can also like look at the diversity of your data, and you can give measure to this data set and find the most like data which is different from your current data. So this is based on diversity. And intuitively, we can give some explanation for these two methods. So, but we want to have a like a more formal like study, and we want to like give a even theoretical characterization for these two methods. So our question is that can we unify them in theory, or can we like give a like a theoretical description for these two methods, and why does this method work, and how does they connect to each other? So this plot shows our like motivation for our research. So our research is based on these two methods for the active learning, especially in the area of deep learning. So it's about like a neural network, and we also want to unify them. So even from the introduction, they are different methods, but we try to unify them to find the intrinsic connection between these two methods in active learning. So before going to the detailed proof, we are going to like give some example, like intuitive example that maybe everyone will encounter in your daily life. So if you are going to prepare your upcoming examples, and what kind of exercise question you want to choose to prepare for your exam. So maybe like you will look for the question or the problems that you lack of understanding. So if you are familiar with and you have like a low confidence on that problem, then you want to like to do more exercise on that question. So this is correspond to the uncertainty. And another one is like, so you suppose you have done a lot of like questions, but some of the questions you didn't like, maybe you just give one or two exercise. So that question may be kind of problem that is different from what you have already done. So you may try to choose diversity. So you want to choose any as many kind of problem as possible. So given this diversity measure. So this is also like for daily life for human beings. They try. This is a strategy that maybe people use for to like prepare the example or like to solve the problem. So this is also correspond to our like studied method in active learning. So let me unify or summarize your strategy. So we want to like learn the knowledge that you are familiar with or you are not fully understand. So this is like ultimate goal of our strategy. So let's so this is summarize the strategies that maybe active learning use. So this is like maybe intuition description for our problem. And now we are going to like to the active learning. So we also have some kind of observation in active learning. So here this plot shows the active learning, the images that you may try to query in your data set. So so we can classify these images into two classes. The first class is given by this blue description, which is called easy to learn. So these lines are very like evident, and this is like a right angle. You can like easily distinguish this what kind of this animal from the first row. However, if you look at the second row, it's harder, right? So we call it hard to learn samples. So these lines, maybe they are like many lines in a group, and they are like maybe playing with each other, or like not the right angle. So maybe some like a strange angle, or like a stranger like pictures here. So also like some other examples shows hard to learn samples. So this is a different kind of like lines. Maybe you are not familiar with, but they are lines. And sometimes we also have some samples like from cartoon or other like format, like with a painting. And in this case, the feature is not so evident, and you are not so familiar with in your daily life. So actually, so in our like active learning scenario for the data for the image classification, we also have this kind of samples. So this is the first step that we can try to use some theory to describe our neuroactive learning. So this is the example. Then we try to give our theoretical description. So before that, we summarize our contribution based on two kinds of active learning method. We want to give a unified theoretical description for this method, and our goal is to prove that these two kind of active learning method want to query yet to be learned features, and this is a key point that the active learning want to perform. And we also like characterize the optimization of the neural network in the scenario of image classification, and characterize the generalization bound for the algorithm post-training. So with theoretical understanding, we can finally unify these two methods and in a single framework. So let's go to like our theoretical part. So from the previous example, we show that your image maybe have like a multi-view, and you have different kind of features in even one image. So this is like an example we can see, like even for a car, you can like identify if this is car by window or view or other like angles. And for cat, maybe you can look at its eye and also like some different features. So actually in the image, we can see that the data has different features and from different view. And here, this is like a hidden representation from a neural network called ResNet34. And we find that this neural network also learns some like features, maybe not so evident, but we can understand as features from the data. So like besides the image itself and the hidden representation, also like learn features from the data. So with this like example, we can like establish a data model to summarize our main factors in an image. So this is like a theoretical setup. Here we have like we call it the feature noise data model, and it is like a multi-patch model. So the first one is we call signal. It's like a vector that try to simulate the main objective in an image. So here Y is a label. So this image is correlated with your label. And the other one is a noise. It's drawn from a Gaussian distribution. So this try to simulate the background. Because this part is like label irrelevant. You cannot determine your label from this background vector psi, which is a Gaussian vector. Then, so this is one of the simplest example. Then we have two kind of like samples features. The first mu1 is easy to learn features that we already shown in the example, and mu2 is hard to learn features. So how can we like define this easy to learn, hard to learn? So simply we can like define the magnitude of the L2 norm of these vectors. So if the L2 norm is small, then we can say it's hard to learn because a corresponding signal to noise ratio is small. And otherwise, if mu1 is like magnitude is large, L2 norm is large, then we can say that SNR is large. We also like can give some frequency to these samples. Like for example, like most samples are contain mu1 features, but just a few samples contain mu2. Then in this case, we can also say that mu2 samples are hard to learn. And we are going to compare like different algorithms. As introduced, we are going to study the confidence and the diversity algorithm. And before that, we are going to introduce like a neural network we want to study. Here is a two-layer neural network. It's one of the simplest convolutional neural network. And here we fix the second layer. We only optimize the first layer. Sigma here is a activation function, and W is a weight vector in the first layer. And these two like from data, and we may call it patch. So these patch are shared with the same weight. Like so, this is why we call it convolutional network. As it is a window that we can from one patch and shift to another patch. And after that, we have the second layer. So our second layer is fixed as either positive one or minus one. So this J takes the value for the second layer, and we are not going to train the second layer, only train the first layer. And the sigma is a activation function, and we use the ReLU activation function in this case. And even we fix the second layer, still a non-convex optimization problem. And so our training loss is logistic loss. And since this is a binary classification, it's equivalent to the cross entropy loss. And the test loss is defined by 0-1 loss, and which is correspond to the test accuracy on the like distribution on the test distribution. And the first, so our algorithm is that we for all of the methods or algorithms, we first have a warm up data set. So it is a small initial data set given by the algorithm, and the random sampling. For random sampling, we just randomly samples from the query pool, and the uncertainty sampling here we define uncertainty, which is by the confidence score for the neural network. So this is so in binary classification case is kind of softmax output. And final one is diversity sampling. For diversity sampling, we try to measure the distance between the query sample, the hidden representation between the query sample and the sample you already learned for the warm up stage. So this is for the warm up stage, and we try to calculate the distance between these two samples. And we try to find the most diverse samples. And here is our theoretical characterization. So to understand the optimization and the generalization, we need to some tool to track the training dynamics for its gradient descent and the logistic loss. So we define the gamma and rho, which is represented for signal learning and noise memorization for the neural network. So remember that we have defined the signal and the noise for the data model, and this gamma and rho is a coefficient for this signal learning and the noise memorization based on our decomposition of their weight vector. So in a high dimensional case, we can prove that these vectors are most orthogonal to each other. So this is a kind of orthogonal decomposition, and they are most independent to each other. So doing the gradient descent, so we can easily track the dynamics for gamma rho. So instead of directly track the W, we study the gamma rho, the dynamics of gamma rho, and we try to understand how does the neural network learn from them. So this is our main theory. The first that, so as introduced in our data set, we have two kinds of signal. One is mu1, which is easy to learn, and mu2 is hard to learn. So after querying, we can prove that for random sampling, it's still like do not learn much mu2, which is hard to learn. So in this case, it have a small test accuracy or large test accuracy on these kind of hard to learn samples. And for uncertainty sampling and diversity sampling, we can prove that the active learning can query as many as possible these mu2 samples, and after that we can succeed learn the mu2 samples, which is hard to learn. And after this, we can show that the generalization error for uncertainty and diversity sampling will be very small given the characterization. So this means that both random sampling and both uncertainty sampling and diversity sampling can sample mu2 from your sample, and until it converges to a like small generalization error. So this is our like theoretical understanding, and here we also discuss some maybe potential extension to our methods to a practical scenario. Because this is like purely like theoretical work, and we give some theorem and to the active learning method to unify them, but we haven't. But we have some like maybe future work that can apply our theory to the more practical scenario. Maybe we can like develop new method, and we can give maybe some instruction for the practical scenario. And finally, so this is like experimental verification for our problem. So this plot shows random sampling. So you can see there is a two-stage behavior. And the first stage is like warm-up training, and the second stage is like a random sampling. So this this red one is for the test accuracy on the hard-to-learn samples. You can see that after querying, you can have a like improvement, but finally accuracy is still small. And let's see the uncertainty sampling. So uncertainty sampling is efficient than these hard-to-learn samples. As after querying, you can see that it's increased to like accuracy to 90%. So this is a huge increasement on these hard-to-learn samples. And the final one is like diversity sampling. So diversity sampling also did a good job of this. So it has the same, the 90% test accuracy on the hard-to-learn samples. So this is this is our like work, and some future work direction we can do based on our current work, and we may like combine our theory with a practical algorithm, and maybe we can also give a more complex data model to handle more complex algorithm and situations. So thank you for listening.
Okay, I think it's time for like the one or two short questions. So
Thanks for the talk. Because we are talking about active learning, I think you start from unlabeled data, and then you want to query some data to be, as you said, that should be most informative, right? But so it's clearly we are doing some labeling, right? But your data generation is still sampling.
So yeah. So this is a good question. So I will let me explain. So first we have like warm up stage. So warm up stage we give like a small amount of samples. So which label is given, and then this sampling that so first like generate like a large amount of.
No, I'm talking about the causality. Because you first have Y and then from Y you generate X.
Oh, you mean the like data model, right?
Yeah, the data model. Because if you are analyzing some supervised learning or semi-supervised learning, then it would be totally fine. Because given some training data in semi-supervised learning or supervised learning, we are not sure whether the data is generative or is labeling or sampling. But for active learning, it's clear that we are doing the labeling process rather than sampling process.
Correct. But for active learning, is we first sample the data. So maybe so this sample does not mean like generate, but query labels.
Yeah,
query samples.
Because you start from unlabeled data.
Yes.
And then you want to select, or you call it a sample. You want to select some data, and then you send the data to human annotators to obtain the label. This is clearly the labeling process.
Yes, this is a labeling process, but here maybe people used to use sampling, so this may be confusing.
Yeah,
but
from the theoretical point of view, there is a huge gap between the algorithm and the problem setting in your theoretical analysis. Then why, after you do some experiments, you can still observe the phenomenon that validate the analysis.
So this is so first the example are based is a simulation. So this data set is simulated from our data model, and we also use a two-layer neural network. So in this case, like we've just follow the theoretical setting.
I didn't get the point. Even if the whole data set is like you first have Y and then you generate X, but still you are running active learning algorithm, right?
Yes. So I mean, so this sampling is not exact sampling in the sense of distribution, but we first query the samples based on confidence and diversity. So this label is not given in this case. And after that,
let's discuss later.
Okay, sure.
Okay, maybe one more question. Yeah. So any question? Yeah, maybe I will ask a very short question. Since you are like mentioning on ImageNet, you are finding the not like, for example, the sample which is worth like the asking. So for example, can you give some example like in the ImageNet? So is this the one you find by your algorithm, or do you just manually pick them?
So we pick by ourselves.
Yes, and can you show like but in your method, did you have any example like similar to this? Like you pick the one which is hard to learn?
Yes, I think so. But here we didn't show, but I think we can do that.
Okay. Yeah. Thank you.
Thank you.
Okay. Thank you for the great talk.
Hi, I'm Yuwei. I'm a visiting researcher at RIKEN and a research scientist at Alaya Research. And today I want to talk about a study in the field of both cognitive science and machine learning. So my talk is about the parallels and the long-term memory to further consider the next step for transformers. So the question of this talk is, can multi-modal large language models learn by just memorizing more and more data? And if we can see these samples here, the association between the discrete symbols, such as the text tokens and the inner knowledge of the visual modalities, is not very established in the current language model. For example, we can see first case, if we want to ask some questions, the model generally cannot understand which part it should focus on. And for the second case, we try to prompt the model to generate some images. Like we want to get an empty glass, but instead we get a glass full of water. So what's the problem of this current cross-modal learning? So these gaps cause hallucination, and we are trying to figure out how to solve this problem. So can we learn by just memorizing more data? Probably not. So on one hand, the transformers are not good at learning discrete information from the higher dimensional perception data, like vision, audio, and other cases. It causes hallucination, inefficiency in training, thus being data hungry. And on the other hand, we know about the neurosymbolic approaches. It offers a more stable way to learn discrete symbols and their relations among these symbols. However, there's also problems associated with neurosymbolic training. So for example, these concepts need to be constantly annotated before we can train these programs. And it's unclear how the different concepts are induced learned directly from the perception data. Even in neuroscience, we don't know that. And especially considering the complexity in the real world data, including this occlusion, complex concepts, and complex things. So it's really hard to decompose these different things into reusable components. Therefore, we consider there's the absence of inductive biases, such as the convolution operation in the convolutional neural networks, and that is missing in the transformers for learning this localized knowledge. For example, in the convolutional neural network, we usually can extract these localized features at different layers. On the bottom left side, you can see the different features can be extracted. But when we look at the attention mechanism in the transformers, we know it's pairwise computation, but it's not like using kernels to focus on localized part of the images at each time. So the transformer lacks the ability to learn these structural features, and it faces challenges in learning from a few samples and require longer time of training to figure out the associations. So that's why it's data hungry and usually cannot outperform the convolutional neural networks in small and medium data sets. So to go into more details, first we consider the vision transformer, and the vision transformer tries to divide the image into these non-overlapping patches. Then we have multi-head attention, try to learn the relation between these different tokens of input patches. So the operation is rather simple. We just have the same input to be used as the value, key, and query. And the point here is we want to focus on the attention weights instead of the final output. And we can try to extract the different weights assigned to these different tokens of the one image sample. So here is the result of the analysis we have done about different layers sparsity after we train the model on data sets. So for each attention head, we can see here I plot from layer 1 to the last layer, and for each layer we have these different attention heads. And for each plot, we show the distribution of how many tokens this attention heads is focusing on. So how to measure this? We measure this sparsity by the minimum number of required tokens whose attention scores add up to 0.9. And we can see there is a very constant patterns in this trended transformer across different modalities. In particular, we can find the 3 different groups. And first group is this blue blocks in the middle of the transformer. And interestingly, these attention heads are usually very sparse. They usually only tend to less than 50% of the tokens. And on the other hand, we have this orange and red attention heads. For these heads, they usually attend to more tokens to solve the task. So the problem here is the sparsity in this token relation is learned implicitly from training data. And so this process is very inefficient and data hungry. So the idea here is, can we introduce an information bottleneck in the attention mechanism to solve this problem so we can have more efficient transformer or attention layers? So the information bottleneck, it tries to introduce the competition among input tokens. So the example here, I show the different patches of images. But I will also talk about if these tokens are from different modalities. So the different tokens are trying to compete to write into the shared space, which I noted with the pairs there. So what are these pairs? So you can consider the pairs are some general assumptions about the samples. When we try to do some perception detection, we use the pairs to guide the attention so that the relevant information can be extracted based on these pairs. And the goal here is how to learn these pairs through the end-to-end training of the transformers. We do not provide the predefined pairs. So this work is also related to the modular neural network. The definition of the specialized neural modules is we can find the correspondence between the strongly interconnected structure components of a model, or you can call it modules, and the specialized function. They usually will be different from each other. And if we can build neural networks that can decompose the perception data into these knowledge modules, it can better adapt to different cases with knowledge reusability. And in animal brain, modularity also favors evolvability and the ability to adapt to changing environments. They can find the common problems across different situations. So the information bottleneck is grounded in the cognitive science studies of the working memory, and especially we are interested in the global workspace theory. So first, if you think about in our daily life, one way we use the working memory, usually when we try to learn in a novel situation, or in other case, we try to take a different approach in a familiar situation. In such case, the working memory will have a limited amount of information it can hold at one time. And the working memory will act as a mental workspace where different information compete to write in the shared space. Since it's limited, they need to compete. And in this process, we usually can get these multiple specialized modules as neural networks and potentially multi-modal. And finally, anything entering the working memory will be broadcast to guide the information process of all the existing modules, including those cannot enter the shared space. And as an extension, maybe in a JSON era, so the working memory also can work hand in hand with other memory systems in the brain for long-term storage. Like we can consider the complementary learning system with the associative memory. In that case, we can use in working memory to learn the pairs, and the pairs will be embedded in associative memory, and perhaps in the hippocampus and we can reuse these pairs later. So in this study, we try to propose a attention layer called the global workspace layer as a replacement to the traditional multi-herd attention in the transformer models. And it can enhance the layer efficiency. So the idea here is we can bring an existing attention layer and just add this very small global workspace layer. And we found that we do not need 12 layers. We just need 6 layers. We can achieve the same performance, so greatly reduce the parameter cost. And also the performance in some cases is even better than larger model. And the proposed method, it includes 3 different components inspired by the global workspace. First is instead of the sample-wise processing, we try to collecting all the tokens in one batch. So for some of you, maybe it's not very intuitive to do such process when we're using the GPUs and all the computing resources, but I will explain how we try to reduce the computation cost. But the benefit is when we do the cross attention, we can attend to different samples at the same time. So the relations can be learned across different samples. A second step is computing the bottleneck attention and selecting the relevant patches to write in the global workspace. And the last approach is anything updated in the workspace will be broadcast to update the information of all the existing modules. So here we can see we have a list of input tokens to enter in the second component here. And the list of tokens, they are all the embeddings of the image patches, and they are all concatenated. And consider these modules compete to write in the explicit memory through a cross attention. And the goal here is to try to find a bottleneck so that only a limited number of tokens can be used to update the memory. And finally, the output of this part is the updated explicit memory. With these pairs we can use for the next time step. So these learned pairs, we'll consider how we can reuse pairs to enhance the representation of the input tokens. So intuitively, we can consider these pairs are these different attractors inside associative memory in neural networks like the whole field network. And when we try to forward these input tokens, we first use them as input to a whole field network. By reducing the energy of the tokens with respect to the learned explicit memory, we aim to enhance the representation by comparing the current input to all the historical accumulated knowledge of the data set. So the whole field network we are using is called the continuous whole field network. And the idea is we have this set of images. And these images will be learned by the whole field network as these attractors in a Bayesian with a Bayesian of attraction. And any input enter a Bayesian will converge to that specific attractors. So usually we apply multiple iterations of the energy reduction to find the attractor. So in this case, if we have occluded images as the input, and based on these attractors, we can change the, basically we have a hyperparameter to change the distance among different attractors. So if the temperature is rather high, we can get a mix of related attractors. And by adjusting the temperature, we can find more crispier images from the process. So in this process, we can try to reduce the energy, as shown in the upper right graph. The patterns are reconstructed over the batch time step, and it shows the generally decreasing trend. And in the lower graph, we show the whole field network, try to fine tuning based on the inverse temperature. And we found that a smaller beta is more likely to result in a metastable state. So it's the Bayesian of multiple attractors. It cannot be disentangled. But on the other hand, if we try to use a very large beta, it usually will result in these identical patches. And here I also want to talk about two problems we encountered by building the information bottleneck into the attention. First one, we try to apply these multiple bottleneck attentions as we use as we select a few tokens in each this bottleneck attention. When we have more and more layers, the information cannot be well stored across different layers. So it leads to the difficulty in forming these spatialized pairs in the later layer. And the result of that is we can say, so here is a collection of different tokens selected by the pairs in the explicit memory. So ideally, we want each pairs in each element in the memory try to focus on a specific part of the images. But eventually, we found that many of these pairs are focusing on the same thing. So this is a problem we want to solve. So in that case, in that sense, we try to propose a loose function to solve this problem. So especially for each token position, we try to compute a cumulative attention loss, which is measured by the total assigned attention scores to each position. For example, we have the attention I, the position I's attention, and it corresponds to different pairs. Then we can get the attention scores between this pair of pair and token. And so for this one, maybe the first and the second pairs are activated, so we can sum up the attention scores and use that as the cumulative attention for that specific location. And the other loose element we used is the frequency of each token position be selected. So it's basically say if it's activated for these pairs, we will have have an additional activation for this specific position. And finally, we try to sum these two types of losses over the different attention heads to get the bottleneck attention balance loss. So we can see the results here. We can observe a noticeable increase in the diversity along with the training. So at the start of the training, usually we can see many repeated tokens selected by the different memory elements, the pairs. But at a later stage of the epoch 80, the more diverse patches are selected by the pairs through the bottleneck. And the second problem is the potentially high computational load of the squash operation that try to concatenate all the tokens in one batch. The benefit of that is we can attend to different features in one batch at the same time, but it also increases the computation cost for the attention weight computation. So to reduce the computation loads, we try to first use the low rank memory So we do not apply the information bottleneck on the original dimension, but try to reduce the dimension to the dimensional D, which is much smaller than the original dimension E. And secondly, we try to limit the capacity to a very small number. For example, in our experiment, we only use 1.6% to 3.2% of all the tokens, which can pass the information bottleneck. So by using these two strategies, we can find that compared to the Wei transformer of a similar size, the proposed methods, which is the AIT, the two different size, AIT base and AIT small, compared to similar size of the Wei transformer, they only have 3% increase in the computation. So how about the performance-wise? And so we can say first compared to the VIT base, which has 12 layers, we have a medium size of the AIT, and it can outperform the larger size Wei transformers, even with better performance. So our study demonstrates the AIT can outperform first these existing sparse transformers, different variants of this, for example, the coordination, and also outperforms the Wei transformers, reducing the parameters needed to achieve a certain level of performance. And of course, the result here are based on the training from scratch without any additional data provided to the model. And the other task of vision language relational reasoning of the sort of clever datasets, we consider both image tokens and text tokens, and they are concatenated, try to compete with each other to enter the workspace. And we found that first, compared to the Wei transformer, in this case, it's much better than the Wei transformer. So in the image classification, it might be slightly better, but in the more complex relational reasoning, like we want to use both image tokens and text tokens, it's much better than the existing approach using the multi-head attention. So finally, to conclude, we propose the associative transformer is try to enhance the parameter efficiency in training the transformer-based models. So to make them more accessible and cost-effective, we try to implement the cognitive science series of the global workspace for a better understanding of human-like relational reasoning. And we are consider other tasks and domains for the information bottleneck, such as audio, video. And we also have some work in safety development of the modular learning, including both priorities and adversary attacks on such systems. Okay, great, thank you very much. I'd love to hear questions.
Okay, yeah, let's thank our speaker. So is there any question? Yeah, yeah, Yichao, yes, please.
Yes, hello. Okay. Thank you very much for the interesting talk. Yes, I'm very interested in the workplace theory, but I can't fully catch the main idea. So could you give some intuitive explanation with something like examples to explain what the workplace theory is?
Yes. Yes, so the global workspace is very related to the working memory. So this graph here shows if we have a local processors is activated, usually it will be broadcasted to activate many other places. And the idea here is first how this local processor can emerge to the working memory, which all of us has only a limited amount of attention. And secondly is if something come up to our mind, how the information in the working memory are used to influence the other modules' parallel processing. So not all the process in the mind you are aware of. So if there's anything in the working memory, that's the only thing we are aware of. But at the same time, there are all the other neural modules are process maybe the other features of the perception data our eyes are looking at. But only the thing, the working memory, will have influence later on this processing. And the global workspace theory basically says we have a limited amount of information can enter a shared workspace. And if the information successfully competes and enters the workspace, it will be broadcast to influence the other parallel processors. So it's also can be considered as a top-down recurrent loop in the attention mechanisms.
Oh, okay, thank you very much. I think I learned more here.
Yes, please.
Thank you very much for your talk. I was just wondering, because you mixing elements in different, which are in the same batch, right, during training, does your method also have some impact on like mixing among batches across in testing scenarios? So does it mean that your elements in your test set are not anymore IID? And does it matter how you sample your batch on the test performance and evaluation?
Let me rephrase that. You mean one try to learn the X-based memory? How do we consider the training batch and test batch? Is the samples, are the samples from the test batch has influence on the memory? Is that correct?
The samples within the test batch, right? So you sample your test batch, you sample your test batch, and usually they are IID, right? Each sample in the batch. What in your case, do they are dependent in terms of your prediction result to each other, or are they independent? So it doesn't matter what are the other elements in your batch for your test, in the test batch.
Yeah. So the task we are considering here, the memory during the training time will not be influenced by the test time. So during the test time, nothing will be written into the memory. And for the independency, so we basically consider the settings like in cipher triangle as the image classification task. So I think depending on the evaluation settings, usually we cannot get much the non-ID setting, right? So it's so from this result, I can only say it's more close to the ID setting rather than the non-ID setting. But during the test time, we do not write any information from the test set into the memory.
Thank you. Maybe you can continue later.
Yeah.
Okay, so since we don't have any question, yeah, maybe we can discuss it later in this, like in the poster session. Okay, I think that we can conclude the session today.
Thank you, good afternoon. I'm Weilong Zheng from Shanghai Jiao Tong University. Thank you for having me here. So today I'm going to talk about rapid context inference in a Thalamocortical model using recurrent neural network. So this is the overview of my research interests. I am quite interested in interdisciplinary between AI and brain science. So how to understand the brain by building the brain, treating the brain, and modulating the brain. And I was a postdoc at MIT working closely with Mike Halasa and Robert Young on modeling the brain. So how to develop a brain-like artificial neural network based on experimental results from neuroscience. So we have one project, and I will focus on this project. And I was also a postdoc at MGH, Harvard Medical School, working with Brandon and Eddie, where we focus on AI for healthcare especially in neurology, where we are working on using AI technologies to analyze different clinical data and to analyze how these variables are associated with patient outcome. And hopefully we can improve the health care. And finally, I am also working closely with Professor Liu on affective brain-computer interaction. And here we would like to develop objective diagnosis and also provide personalized treatments for some psychiatric disease like depression. And Professor Liu has already introduced some of our work yesterday. And due to the time limit and also because the topic of our workshop is about brain-like computing, so I will mainly focus on the first topic, modeling the brain. So how can artificial neural network help us understand our brain or minds? Actually, nowadays, we can see increasing interest between neuroscience and AI, all right? And artificial neural network has been widely used in different neuroscience research. And it can be used to analyze different data. And also it can help us model complex behaviors and different neural activities. And also it can help us understand the neural circuits in our brain from optimization perspective, right? So why we would like to model the brain? Well, first, it can help us understand the mechanism of our brain, and hopefully we can develop a unified computational framework of our brain. And then we develop the brain-like intelligence algorithms, and hopefully it can be beneficial for our future clinical application to treat different brain disease. So here I'm going to talk about one project about cognitive flexibility. So first, what is cognitive flexibility? It's an important characteristic that enables animals or humans to selectively switch between sensory input to generate appropriate behaviors. Actually, how we respond based on the current surrounding environment or the context, right? For example, when my cell phone rings, I usually answer it. But if my cell phone is ringing right now during my talk, I will quickly mute it. So in both cases, the sensory inputs are the same, but how I respond change, right? Depending on the current context. So this is called the cognitive flexibility. It's a key intelligence in humans and animals. So previous studies have shown that the prefrontal cortex, the PFC, plays an important role in cognitive ability. The PFC receive the inputs from many brain regions, from other brain regions, and also send outputs to these brain regions. And also a recent study from Halassa Lab show that the medial dorsal thalamus, MD thalamus, also highly engage in this cognitive flexibility with the interaction with the PFC. So this is the interaction between the PFC and the MD. And this is a study published in Nature Biotechnology showing the highly dense projection of the MD to the PFC, right? So based on this highly dense projection structure, there must be some interesting computation between the PFC and the MD. So our goal is to find a computational model of this thalamocortical interaction. And for computational modeling, people usually use a recurrent neural network for modeling the PFC. However, in this study, only one brain region is modeled, usually for PFC, for example. So, but we know where the different brain regions are highly interacted, right, during the cognitive process. So one interesting question would be how to develop a multi-area artificial neural network and design a learning rule between different brain regions to capture this diversity during different cognitive process. So our work is actually inspired from this Nature Neuroscience paper, a RIKEN paper. And this paper is about thalamocortical interaction during decision making. So they design a task. A mouse selects between two spatially conflicting targets. One is the visual target and the other is the auditory target. And this selection is actually based on one of the two learned cues, low pass noise and high pass noise during the delay period. So another two cues, UV flash and green flash, are introduced to assess how the mice switch from one context to the other context. Low pass noise and high pass noise are presented in one block as context 1, and UV flash and green flash are presented in another block as context 2. So from their experimental results, they actually find that first, the PFC neurons have mixed selectivity, meaning that some PFC neurons are cue selective. These neurons only respond to specific cues, while some other PFC neurons are cue invariant. They only respond to specific rules. For example, this PFC neuron only responds when the mice attend to vision. And interestingly, they also find that the medial dorsal thalamus neurons can selectively encode temporal context. For example, in this figure, one MD neuron only responds in the first block, encoding only context 1, but not a response in the second block in context 2. So based on these experimental results, they propose a computational framework to model this interaction. So in this framework, the MD neurons gain these context selectivities by integrating the PFC neural activities, right? And they suppress the context irrelevant PFC activities. So inspired from this work, we aim to develop a multi-area neural network to model the neural computation between the PFC and the MD. So here is our model framework. Suppose that we have 4 inputs corresponding to 4 cues in the experiments. Low pass noise, high pass noise, UV flash, and green flash. And for each trial, only 1 cue is presented. So in the middle, we have 2 components, the PFC and the MD. And the PFC is a recurrent neural network. And for each trial, only 1 cue, one stimulating, only 1 input only stimulating a subset of the PFC neurons. And we need to develop a PFC-MD learning rule between the PFC and MD so that the MD can infer the current context which context the PFC is learning right now. And there are 2 output neurons corresponding to 2 rules, attend to vision and attend to audition. And the output ways are learned in a supervised way. So let me introduce the details of each component. So first, the PFC. It is a reservoir recurrent neural network. And here is the PFC neural dynamic with exponential decay. For each PFC neuron receives 3 inputs. The Q input, the recurrent input, and the MD gating. And there are 2 effects. There are 2 MD effects on the PFC modeled by the multiplicative term and the additive term. I will introduce the details in my next slide. And the MD is modeled as a feed-forward network receiving the PFC neural activities as the inputs. For the output, the readout unit are separated from the PFC, the recurrent neural network, and receiving the PFC neural activities as the input, and then predict the rules, attend to vision or attend to audition. So I just said there are two MD effects model in our framework, a multiplicative term and additive term. And the multiplicative term models the mediation of the MD on the PFC. It tries to enhance the recurring input for the context-relevant neurons, relevant PFC neurons. And for the additive term, it models the inhibition of the MD on the PFC. So these neurons are context irrelevant. You need to suppress their neural activities. And for these neurons, it is context relevant. So you need to amplify their functional connectivities. So these two MD effects actually are very consistent with recent findings of two distinct MD cells. They find two MD cells called DRD2 and GRID4. DRD2 amplify the functional connectivity, so the multiplicative term, and the GRID4 MD cells suppress the PFC neural activities, which is modeled by the additive term in our formulation. So another problem is how to design a learning rule between the PFC and MD, right? The PFC and MD synaptic plasticities. So here we use Hebbian learning. So, different from Hebbian learning, which just use the instance presynaptic and postsynaptic activities. Here we use the traces to calculate to update the synaptic weights between the PFC and MD. So we use a presynaptic trace to extract the context information by integrating the activities over trials, because the context information are stored by the activities over trials, right? You see you represent the stimulants, right? Again and again in the same block. So they are stored by the activities over trials. And for the postsynaptic trace is to stabilize the MD outputs when the cues within the same context are switched. And these are the formulation for the weight update. And this is the calculation for the presynaptic trace and postsynaptic trace. And we use top K normalization in the MD. For the training paradigm, we train the model, train the network first with context 1 and context 2, and then switch back to context 1 to see how it performs when it meet the previous context. And here are the PFC and MD neural activities in context 1 and context 2. And then this is the decoding performance of the PFC and MD. These are the learned synaptic ways between the PFC and the MD. And we add different noise to this model, and we can see that this context encoding is very robust to different noise. So what are the computational advantage of adding such a MD module to a neural network? Well, first, it can flexibly switch between queuing contexts, which is very important for continual learning. So this is the model performance. We can see that with the MD, the PFC and the MD model can have a very low prediction error at the context switch, right? Which means that the model, the PFC and MD model, can alleviate the catastrophic forgetting. So traditionally, standard neural networks usually suffer catastrophic forgetting. For example, when we train a neural network on a totally new task, right? It will totally forget what it has been learned before and change all the parameters. So it will totally forget the previous knowledge. But in our model, because of the MD effect on the PFC, it will amplify the context relevant neurons activities, right? And at the same time suppress the context irrelevant neural activities. So making the PFC neural activities more modular for different tasks, right? So the PFC neural activities are less interference across different contexts, which can achieve continual learning. And the PFC model also enable efficient population coding in the PFC. With the MD, we can see that the PFC MD neural activities are more sparse, saving more energy in computation. And the PFC MD model also reduce weight changes in context irrelevant neurons. From this figure, you can see that with the MD on, the model only focuses on updating the weights of current context neurons and protect the weights of other context neurons, protecting, so it has a weight protection mechanism. So I have shown that this model can perform well in a simple task, right, without too much dynamics in the PFC. So next, we would like to scale up the model and to see whether it can also generalize to other more complex cognitive tasks. For example, the working memory task, the decision-making task, and so on, other complex cognitive tasks. But this is particularly challenging because the model needs to infer the temporal context online, but at the same time, it needs to do this complex task learning at the same time. So combining the context inference and task learning together is very difficult. So for example, here I show an example here. Different set of neurons could be activated within the same trial and also across different trials. But the trace computation in my previous synaptic plasticities, right? The trace computation cannot guarantee to cover all the possible target neurons in this task. So making this context inference very difficult. So to deal with this challenging, we propose a new form of this thalamocortical interaction by introducing a new module called PFC context. So we separate the context learning and context inference and task learning into two pathways. The task learning pathway optimize with supervised learning through this PFC, and this is the context inference pathway. So from this pathway, it will regulate the PFC neurons, like the amplifying context relevant, suppressing the context irrelevant, and here doing making it more modular for different tasks. So we also compare our model performance with real experimental results in mice. So this figure, panel D, shows the experimental data in mice when the mice are also performing similar context switching task. And by inhibiting the MD, we can see that the mouse performance also drops when they switch back to the previous context, the learned context. And panel E is our model performance, right? And similarly, by inhibiting the MD, the PFC model, the performance also drop when the model switch back to the previous learned context. So these results are consistent. Our model performance are consistent with the experimental results in mice. And we also compare our model performance with other continual learning baseline. For example, the EWC-SI algorithms. And our model performs better than these baselines. So for this slide, I would like to show the forward transfer. Besides continual learning, right? We also usually would like the model transfer the knowledge of previous learned tasks to new tasks. This is called forward transfer. Not only continual learning, but would like to transfer the knowledge of old tasks to new tasks. So to enable our model with this ability of forward transfer, we allowed the MD projection to be overlapped, right? To overlap, and different cognitive tasks can share a common subset of the PFC neurons. So this is shared in different cognitive tasks. And also, they have some private subsets for the individual cognitive tasks. And we measure the similarity between different tasks, right? So here are our results. With increasing the task similarity, our model, the PFC-MD model, can achieve a higher or increasing forward transfer performance, while still maintaining a good continual learning performance. So it can achieve forward transfer, but also maintain the continual learning performance. So in summary, in this study, we developed a computational model for thalamocortical interaction in cognitive flexibility. And we have shown the computational advantage of this model. And to further develop a brain-like artificial neural network, we need to combine both the bottom-up biological knowledge with top-down computational goals, so that this brain-like neural network can scale up and generalize to more real-world applications. So I would like to thank my lab members and also my supervisor, Mike Halasa at MIT and Brandon Westover at MGH, and Professor Rui at SJTU. And thank you for your listening.
Thanks. So any questions? Yeah.
Thank you for the great talk. I'm wondering, do you have any like the wet experiment result to support your finding?
Right. Yes. We have a direct comparison here. Here, the panel D is the experimental results in wet experiments. This is the experiment result from mice. When we inhibit the MD neurons, the performance of the mice dropped, right? When they switch back to the previous context, the third block switch back to the context. And similarly, this is our model performance. When we inhibit the MD module, which we call the PFC-only model here, the model performance also are degraded when the model switch back to the previous context.
So do you find any evidence on the neural connectivity? For example, more biological way, for example, their protein change or the inhibit like some like the chemical change?
They're actually in the other Nature or Nature Neuroscience paper where they only focus on this the response of different MD.
So do you can we call you find a new circulation or you find a new path or?
We develop a computational model of this, modeling this different.
In biological way, can we call you also find a new biological path in?
No, I don't think we find the new pathway. Actually, our work is inspired from this from the previous paper they find, for example, new types of MD cells, right? For example, the DRD2 MD cells and the Grifo cells, they have different MD effects on the PFC. And we have our computational formulation for these two MD cell types.
Okay,
Yeah.
so sorry for one more question. So have you tried to induce the mouse with depression and PTSD, and then to see like whether they find this continual learning?
Right. This is a very interesting question. Actually, why they would like to develop or would like to investigate this study, like the PFC-MD interaction, because they find that actually the MD not only relay the signals, but also engages a lot of connections, like some psychiatry disease also. So they want to find the mechanisms of this disease and hopefully try to find a solution to that. But here we just propose, we would develop a computation model for this interaction that are fine in the wet experiments.
Okay, thank you.
Thank you.
Thanks for next question.
Thank you for the wonderful talk. And just following the slide, so my intuition would be that top-down connection in the brain is mostly inhibitory. If you want to be flexible, we have to inhibit a lot of kind of inputs, like decision-making would be related to inhibition. And in your model, when you suppress PFC, also the
suppress the MD.
MD.
Yeah, suppress. Yeah, you are right. You mean this one,
yes,
the PFC?
Yes.
For the PFC, we inhibit, we remove the MD module, right?
Okay.
Just keeping the PFC. So there are no MD effect on the PFC. So there's no suppression, there's no amplifying, just one PFC module performing different tasks.
Okay, thank you.
And it's just like the standard neural network, right? One neural network, when you learn a task, and then you switch to the other task, it will totally change all the parameters. So this is why the performance are degraded. But with the MD effects, it can amplify the context-relevant neural activities and suppress the context-irrelevant irrelevant neural activities, making them less interference.
Okay, thank you. Great.
Okay, because the time constraint, so let's thank Professor Zheng again.
Yeah.
My name is Yujin at U Tokyo and RIKEN AIP, and I'm very glad to have the opportunity to present our work. And our research is about learning theory on in-context learning by transformers, named Transformer Efficiently Learns Low-Dimensional Target Functions in Context. This is joint work with Kazusato in U Tokyo AIP and Professor Suzuki, and Denny Wu in New York University and Flatiron Institute. So first, we briefly introduce our background called ICL, in context learning, which is an important concept in large language models. ICL is a learning paradigm where pre-trained large learning models can recognize patterns in few examples in given prompt. For example, when ChatGPT is given few examples where output is the sum of two numbers in input, then ChatGPT can correctly answer the new input corresponding to the query. The remarkable aspect of ICL is that it typically only needs very short prompt. For example, we can consider preparing new MLP and consider training MLP using this context as samples. But if we do so, very, very long context as samples will be needed. However, transformers only typically needs few samples. Therefore, a natural question is that why transformer can learn from shorter context without updating parameters in inference time. So we mentioned about some existing works. In learning theory, doing linear regression in context is extensively studied. The main finding is that pre-trained transformers emulate linear regression on the context. So for example, if transformers are fed context composed of inputs and outputs, where output is a linear function of input, then linear transformer can emulate linear regression on these contexts. However, linear regression is linear regression with optimal regularization parameter is known as such as Bayesian optimal. It means that this is optimal in terms of sample complexity and generalization error. So under their settings, pre-trained transformer cannot run on shorter contexts than rich regression. So it can be said that these settings cannot fully explain few-shot learning feature. So our main hypothesis is in this research is as follows. If the problem has some structure, then transformers can adapt to it by pre-training and significantly reduce the context complexity. So more specifically, we considered learning nonlinear function specified later, whose problem distribution is only supported on low-dimensional subspace in full space. And if the inner dimension is R, which is much smaller than D, then we showed that transformer only requires context length only depending on inner dimension R. And this assumption of low-dimensional problem distribution is a modeling of the situation. For example, meaningful relation in natural language is limited to very small space in the full space of every random chain of words. And it is also empirically observed that if we consider linear regression whose true vector lies in low-dimensional subspace, then transformers' performance adapt to the low dimensionality. But our novelty is that we considered nonlinear setting and derived end-to-end generalization error analysis in this situation. So let's explain our problem setting specifically. Our in-context dataset is composed of input X and output Y. Here, output Y is decided as follows. First, we take inner product of some feature vector beta star and input X, and take nonlinear function sigma star specified later. Then this form of function is called single index model, and its sample complexity as a baseline is very well studied in the literature of feature learning. We suppose that support of beta, which is d-dimensional vector, only lies in r-dimensional subspace of D. This is our low-dimensional assumption. Moreover, we suppose that sigma is some kind of random polynomial, which has a form of Hermite expansion, where Hermite polynomial is this kind of orthogonal polynomials, whose quotient is randomly taken. But why we use such Hermite expansion form? Indeed, the sample complexity of several baseline algorithms, such as kernel methods and neural networks, has close relation to the Hermite expansion of true function. Now, suppose sigma is degree p polynomial, and its Hermite expansion is as following form. Then we define a value called information exponent as the minimal number whose minimal degree whose coefficient is non-zero. So for example, information exponent of LMIT 2 and plus LMIT 3 is 2. And it is shown that sample complexity in order to achieve order 1 generalization error is order of D2P for kernel methods and order of D2 information exponent for gradient-based methods on neural networks. And we showed in our theorem that pre-trained transformer only needs R2P in context examples. So if R is very smaller than D, our theorem shows a great advantage of transformer in terms of context complexity. So remark that in our case, information exponent changes because the coefficient is random. So this is a modeling of a situation where the difficulty of tasks are diverse. So based on this problem setting, we briefly state our student model. We basically use linear attention module, MLP two-layer module followed by linear attention module. We don't go into the details, but linear attention equation is defined as follows. And in embedding of linear attention, we use the output of each neuron of two-layer neural network. And we construct estimator of the output corresponding to the query using the right bottom entry of this output of linear attention module. So finally, the estimator of YQ has 3 parameters, W, B, and gamma. W and B is a parameter in neural network, and gamma is attention matrix, which is in linear attention. And we train this model in 2-stage algorithm. First, we draw T1 data in context data with context length N1. And we conduct one-step gradient descent with respect to the MLP weight. One-step gradient descent seems very tricky for you, but this is some kind of common remedy for treating non-convex structure in feature learning problem and used in some literatures. And next, we newly draw T2 data with context length N2 and conduct rich regression with respect to attention matrix gamma. This is convex and optimal value is obtained efficiently. So we conducted end-to-end generalization error analysis on this training procedure. For validation, we use ICL disk. This is expectation of deviation of true output and estimator. And the expectation is taken over context whose length is n star. In other words, we calculate test error using a context length n star. So the problem is how many n star is needed to achieve low test error. And we state our theorem. Let F be the transformer pre-trained using 2-stage algorithm we said before. And let T1 and N1, which is a prompt length and number of tasks to use pre-training, in pre-training. And then Rn star is our generalization error, and tau is noise level. So the deviation from noise level and generalization error can be written as follows. This is a little bit complex, but please recall that T2 and N2 was pre-training task complexity and context complexity. And our most interest is N3, which is the context complexity in inference time. And we can show that in order to achieve order 1 small ICL risk, we have to only prepare context length which scales with inner dimension R, which does not depend on full dimension D. So in contrast, kernel methods or neural networks, when trained directly on context, need D2P or D2I context. So if R is much smaller than D, transformer is more and more efficiently grasps this true function efficiently. So let's briefly go into the sketch of the mechanism. So in proof sketch, how can transforms adapt to the low-dimensional subspace? So the proof sketch is divided into 2 parts. First, in stage 1, that is one-step gradient descent on MLP, MLP parameters aligns with the R-dimensional subspace. That is, before pre-training, each neurons is in a random direction. But after pre-training, it aligns to the R-dimensional subspace, which beta is supported, where beta is supported. And then attention layers can approximate the link function with row norm efficiently, thanks to this alignment phenomenon. So first, we can show that MLP layer can achieve alignment to the true subspace. We omit the detail for the limitation of time. We can decompose the empirical gradient of its expectation and the noise from the expectation. And we can show that if data is sufficiently large, noise is sufficiently small. And moreover, this expectation is almost in the R-dimensional subspace. So we can show alignment phenomenon. And we mentioned about recent important update. If in our case, the information exponent was from 2 to P. And in this case, we only need T, T is D to 4 and N is D to 2. However, if the information exponent is generally Q to P, we could show that T complexity of task number is D to 2Q. And complexity of the context length of each pre-training task is only D to 2. So task complexity for alignment is governed by the lowest information exponent, but we don't need to scale context complexity in response to information exponent. We skip the approximation result of attention layer for the limitation time, and we proceed to conclusion and the experimental result. So in conclusion, we conducted analysis of ICL on single index model with low-dimensional structure and shows that by pre-training, parameters can align to the low-dimensional subspace. And then they only require context length depends only on inner dimension. And important future work lies in the regime of high-dimensional structure. That is, when R is very near to D, our context complexity is D to P, which is the kernel method's sample complexity. But we, of course, expect that pre-trained transformer can learn features. That is, even if R is very large, acts similar to neural networks. So And our hypothesis is that we need more layers to achieve D to K, D to information exponent when R is near D. So this is one important future work. And we briefly mentioned about experiment. This is comparison of generalization error using degree 2 Hermite polynomial, where true direction is drawn from two-dimensional subspace. And we can see that using transformer, we can achieve low test error even using shorter context. That's all. Thank you for listening.
Thanks for this great talk. Welcome. Any questions?
Thanks for the talk. I have a very stupid question. So in the beginning, you gave an example using GPT-4 to solve the problem. I don't know why this is the in-context learning there is related to your in-context learning.
In the first.
In the very beginning.
This one? Yeah.
This one. Because, so why 32 is the correct answer?
In this case, the answer is the sum of two numbers.
I know that, but I'm a machine learning researcher. So I don't think 32 is the only correct answer.
I see.
Because you already put some very strong prior. You prefer simple, like if some rule is simple, you think it is the ground truth. Because you only gave 5 equations, right?
Yeah.
So any polynomial with
I see.
with more than 5. Yeah, first of all, as a human being, I think 32 is the correct answer. But as a machine learning researcher, I don't think 32 is the only correct answer. And I think GPT-2 can solve this. Like as you mentioned, in context learning, or you call it few shot learning, it's because it's in the training data of GPT-4. I don't know which version you use. It sees a lot of similar example. This is in context learning, but more importantly, the large language model already knows the concept of summation. So it quickly recognizes this is summation. But in your analysis, I think you didn't consider this point. There is some logical things inside, but you only consider the statistical perspective of in-context learning.
But this phenomenon where transformer can recognize summation can be interpreted as so meaningful relation is limited in the full relations, such as there might be the most
because from this example, we can see that the GPT-4 or 3 can not only give the correct answer, but also give us the reason to convince us that this is correct answer. That's very, very important. But if you pre-train, in the latest SML, Alan Zhu, Zheng Zhu gave a tutorial about training GPT-2 from scratch, using only the middle school, the high school math problem. Then maybe if you don't add some prior knowledge, teach the GPT-2 what is called a summation, maybe the model can still give correct answer, but it cannot give answer in this way.
Okay. So do you mean that GPT-2 learns something from in-context pre-training examples? Because pre-training examples includes much examples of summation.
That was exactly my point. If the model only says the correct answer for this problem is 32, I think it may be the reason you have explained in your talk. But we can see that it says the pattern in the given pairs of numbers appear to be the sum of the two numbers. This cannot without a very huge training data set. The model cannot answer in this way. It can only give the correct answer because it observes, it really uses the mathematical or statistical in-context learning. But in this case, it does not really use the statistical in-context learning. It refers to some knowledge base which have some like a Wikipedia.
So yeah, that's an interesting viewpoint, and why the transformers extract some semantics from in pre-training examples are actually not solved well. So it should be put on some mathematical foundation. Yeah.
Okay. Okay. Very interesting talk. And once you consider lower dimension, as your conclusion page said, that lower dimension in the parametric space, not in the embedded space, because you found the parameters are found a lower dimension subspace. Generally, we saw that the representation in lower dimension space is in embedded space. But here you mention space, what is the different lower dimension? Your constraint is learn the model in parameter in the lower dimension space.
Yeah.
So what is this lower dimension implication? So if we consider embedded space, the neuron vector space, that is meaning that our feature is in lower dimension space. But here you mention in lower dimension, what is the some implication from this lower dimension space?
Yeah, this is slightly different from the standard low dimensional structure in feature. But so in this case, we are considering some multitask learning, which so say task has some diversity. But we are considering the situation where task is not so diverse. So task is diverse, but limited in some subspace. And so this is some analogy to the real situation, because we have diverse tasks, but a meaningful task is limited to the lower dimensional subspace.
Okay, thank you.
Okay. Thanks again for this great talk. Due to time limitation, then we can discuss more.
Thanks for the introduction, and hello everyone. I'm Yilan Chen from Deep Learning Theory team. I'm an intern at the Deep Learning Theory team and a PhD student at UC San Diego. These are my wonderful collaborators. So this talk will have three parts. First, the equivalence between neural networks and kernel machines. And the second, analyzing generalization of neural networks through loss path kernels. And finally, conclusion and future works. In the first part, we will talk about wide neural network and neural tangent kernel, and general neural network and loss path kernel. So a kernel is defined as an inner product of some feature mapping for two data points. Here, the phi is a feature mapping that maps the data to a potentially infinite dimensional feature space. And the kernel machine is a linear function in the feature space. For example, here the G is a linear function for the phi x. The beta is a weight vector for this linear function. And the kernel machine has a good property that the weight vector, this beta, can be written as a linear combination of the training points. So using this property, we can write the kernel machine as a linear combination of the kernel function. So instead of the compute the feature, which can be infinite dimension, we can instead compute the kernel function, which is a scalar. The RKH S norm of the kernel machine is just the 2 norm of the weight vector. Then the neural tangent kernel is introduced by Jacob et al. In 2018. It's defined as the inner product of the gradients for 2 data points. Here the F is a model. And this NTK measures the similarity between data points by comparing their gradients. And this shows that under suitable conditions, for example, infinite width limit and NTK initialization, NTK at initialization converges to a deterministic limit and keeps constant during training. So here, at the initialization, this function should depend on the specific parameter of the network. But in this condition, it will converge to a function that are independent of the specific initialization. Then people show that infinite width neural network trained by gradient descent with mean square loss is equivalent to a kernel regression with this NTK. So here the kernel regression is just as a linear regression in the feature space. And then Li et al. Showed that while the neural network are linear in the parameter space, so basically the model can be well approximated by the first order Taylor expansion. The difference decreases with the width of the neural network. Then one of our papers shows that infinite width neural network trained by L2 regularized loss is equivalent to a L2 regularized kernel machine with NTK, for example, SVM. So we show that if we train a neural network with a standard loss function plus a regularization on the last layer, it's equivalent to a kernel machine. So here the kernel machine is a linear function using the gradients as a feature and train it with a L2 regularized loss function. For SVM, we just use a loss function as a hinge loss. So we verified this equivalence in the experiment. Compared to previous equivalence with a kernel regression with NTK, we have now new equivalence including the SVM and the soft margin SVM. And under some condition of the loss function, we can show that the difference between the neural network and the kernel machine decrease with the width of the neural network. So far we show that while the neural network are either equivalent to a kernel regression or L2 regularized kernel machine. These equivalents are very useful for analyzing neural networks, but they only hold for infinite width or ultra-wide neural networks. And the NTK as a fixed kernel lacks the ability of feature learning. And also NTK has a performance gap compared with practical neural networks. So the question is, can we establish an equivalence between general neural networks and the kernel machines? So in this work, we show it's possible to do that. So let's consider the gradient flow. It's just the gradient descent with infinite small learning rate. And we define a new kernel function called the loss path kernel. This loss path kernel is defined as the inner product of the loss gradients for 2 data points and integrate over the training trajectory. So for example, here, the parameter starts from W0 and trend to W capital T. And at each time, each point, we compute the loss gradients for 2 data points and compute the inner product between them and integrate over this training path. With this LPK, we can show that the model trained until time capital T, its loss function is equal to a kernel machine with this loss path kernel plus the loss function at initialization. So this is a very general equivalence because we don't require the width of the neural network And it even holds for any parametric model trained by gradient flow. For stochastic gradient flow, we have similar results. Because for SGD, we can treat each step as a 4-batch gradient descent. So each step is equivalent to a kernel machine with this LPK. And the SGD, the final model will equivalent to a sum of the kernel machines. The summation is over the training steps. And we verify this equivalence. Here we compute the difference between the loss of the model and the kernel machine we derived. So here's a different line plots the loss for different samples. And here we show that the neural network trained by gradient flow is exactly equal to the kernel machine. And also the neural network trained by gradient descent is also close with this kernel machine. Compared with previous equivalence results, previous NTK only holds for ultra-wide neural network for mean square loss. Our previous work holds for ultra-wide neural network and L2 regularized loss functions. And this work is much more general, holds for general neural networks. So we have these equivalence results between neural network and the loss path kernel. So how this can be useful? So here we show that it can be used to analyze the generalization for neural networks. In generalization theory, we are interested in the generalization gap between population loss and the training loss. Usually, people prove that this generalization gap is upper bounded by the size of the function class and decrease with the number of training samples. For general neural networks, for example, VC dimension, it increases with the number of parameters of the neural network. And the norm-based bounds increase with the norm of the weight matrix. These results are very general, but they do not explain the generalization ability of over-parameterized neural networks because the number of parameters and the norm of the weights can be usually is very large. And these bounds are usually vacuous, too large to be useful. And for ultra-wide neural networks, people also proved generalization bounds based on this infinite width NTK for two-layer fully connected neural networks and also for deep fully connected neural networks. These bounds are tighter than the general theory, but they only hold for ultra-wide neural networks. So the question is, can we establish tight generalization bounds for general neural networks? So here we try to use equivalence we derived between neural network and LPK to derive generalization bound for general neural networks. So here first we define because different training set will train to get a different loss path kernel. So we define a set of loss path kernels with a constraint on its norm. So here the S prime is any set of data points. And this KT S prime is the loss path kernel trained from this set of data S prime. And this set KT is includes all the possible loss path kernels and with a constraint that satisfies this constraint on its norm. And then we define a set of neural networks trained until time capital T. So here this set capital GT includes the functions of this small gt, small gz, So because of the equivalence we proved, each of these functions corresponds to a loss function of the neural network trained from a possible training set S prime. So the intuition of our work is that the whole set of neural networks can be very large because it includes all possible neural networks. But the trained network can only converge to certain small set of neural networks. For example, the network starts from this W0 and trained by S1 prime. It converges to a point WT. And if it is trained by another training set, S2 prime, it converges to another point. And at each time, we will have a set of neural networks. At time capital T, we have these trained networks. The intuition is that this capital GT only contains possible trained neural networks, and it can be much smaller than the whole set of neural networks. And we characterize this GT through the equivalence between neural network and the kernel machine using the loss path kernel. Then we compute the Rademacher complexity of this GT to derive a generalization bound. So here we get a generalization bound that can be computed with this loss path kernel. It has two terms. The first term measures the magnitude of the loss gradients throughout the training trajectory. Because if we take into the definition of the loss path kernel, it's the first term is just calculate the norm of the loss gradients and integrate over the training trajectory. And the second term calculates the range of variation of the loss path kernel in the set of kernels. So this bound shows that the generalization of neural network actually depends on its training trajectory. And for a fixed training set, neural network converge faster and with smaller loss gradients will generalize better. Because this bound shows that the generalization gap depends on the loss gradients over the training trajectory. And intuitively, neural network changes less from initialization, is less complex, and has less chance to overfit. Then we estimate our bound on a two-layer ReLU network, and we show that our bound is very tight compared to previous both VC dimension and norm-based bounds and NTK-based bound. Compared with previous generalization bounds, VC dimension and norm-based bounds are very general, holds for any neural network, but they are usually vacuous. And NTK-based bounds are tighter, but only holds for ultra-wide neural network. Our bound is more general and also tight at the same time. With this general theory, we can apply to derive improved generalization bound for infinite with neural network. So here we show a bound for infinite with neural network that's better than previous bound. And it can also be applied to applications such as neural architecture search. So here we use our bound to estimate the test loss and design minimum training loss algorithm. So here we define this metric using the training loss and plus the generalization bound we derived. And we calculated this metric at the initial training stage to predict the performance of the network architecture. And we show that our algorithm can perform better than previous NAS algorithms. Finally, the conclusion and the future works. So first, we have some new equivalence between neural network and the kernel machine. For example, the equivalence between wide neural network and the support vector machine. And the NLPK equivalence that holds for general neural networks. And we also have generalization bound for general neural networks that holds for general neural networks and is very tight at the same time. And our theory is useful in both in theory and the practice. We can derive better bound for ultra-wide neural networks and design minimum training NAS algorithms. For future works, we can consider some applications based on the theory. For example, we can analyze different neural network architectures from this equivalence and design better kernel function based on this LPK. Because this LPK is learned from the neural network, it should be better than traditional fixed kernel function. And it can also be used to utilize, quantify the influence of each training sample, which could be useful in call set selection, interpretability, and robustness. The second point is we can consider equivalence with for other optimization algorithms. For example, SGD with momentum and Adam. And we can also improve the generalization bound to get tighter and meaningful bound. And in this paper, in this work, we only defined the LPK and we didn't study the process of the LPK, how it's learned, and what's the formulation of this LPK. So maybe we can do some fine-grained characterization of this LPK. So next is some another work we did. We did some theoretical analysis for the dataset distribution. So I will skip this part. Thank you for listening.
Yes.
No question?
Thank you for the talk. Can we go back to the definition of LPK?
Yes.
Because I think the result is very strange or not strange, because in the definition of LTK, you have some integral. Right?
Yes.
From 0 to t.
Yes.
Capital T. Data is not appeared in NTK or mean field analysis.
Yeah, it's not NTK.
Then as a result, not only neural network, but any model that is continuous is equivalent to kernel machine.
Yeah,
I think this is the data linkage. This is conceptually the same as data linkage because you have already seen the training process. And then you use the training process you have seen to define a kernel. Yeah. And then not only neural network, but any model, any machine learning model that is continuous is equivalent to kernel machine because you use this to define the kernel.
Yes. So basically, this equivalence does not depend on specific model you use.
Yeah. So I can say nothing surprise. All this is in fact data leakage.
Data leakage.
This is conceptually same as data leakage. This is like a training dynamic leakage. Because I don't deny it's a kernel function because it must be positive, definite. But the issue is that when people define kernel function in traditional machine learning or even in NTK, you cannot first see the training process and then define a kernel. There is causality. You first define the kernel and then train the model with the kernel.
I think it's not necessarily first define function, kernel function. So traditionally they did it that way, but that doesn't mean
traditionally they did that way. They just don't put it as a rule. But there is really some causality because if you have already seen the training dynamic and then define a kernel, anything is a kernel machine.
Yes, so
this is too general. This is pseudoscience, you know.
So the purpose here is with this equivalence we can study
I know
the
technically
training process.
it's meaningful, but philosophically, this is very like a pseudoscience, because anything is kernel machine. You cannot find a counterexample in machine learning. The model is continuous and it's not a kernel. It's not equivalent to kernel machine.
Yeah. So
I think that's the key difference between NTK and LPK. Because in NTK, you said that there are some limitations. They can only handle infinite wide or ultra wide neural network. But I think that's a key feature, because like any theory should have some applicability. There is a domain. Inside this domain is correct. Outside the domain, the theory is incorrect. That's theory. That's science. But in your case, anything is equivalent to a kernel. You also mentioned that.
Not anything, because we require it to be trained by gradient flow. So
yeah, I understand that. But your claim is not a gradient flow. Your key point is that any neural network is equivalent to kernel machine. The condition is that if it's trained by gradient flow. But my point is that any machine learning model that is continuous, if it's trained by gradient flow, is equivalent to kernel machine.
Yes.
This is too strong, because you have already seen the training dynamic and used the training dynamic to define the kernel. It's like you have seen the future.
But in practice, you always train your model, right? After you train the model, you get the train. You say the model.
But for NTK, it's something like that. Before I training the model, I know it's equivalent to a kernel machine. But now it's like after you train the model, you know it's equivalent to a kernel machine.
So I think so. In this work, we mainly want to make the theory more general. So we haven't. We are still trying to study more specific case to do some case study. In some specific case, we may analyze this LPK more in detail, and we may derive some like closed form expression for this LPK. In that case, maybe we don't need to train the model to get the LPK. Instead, we can get the LPK before the training stage.
But then is it still LPK? Because you use.
Yeah, so in some case, maybe you can analyze the optimization process, and you can calculate a closed form solution for this integration.
Okay. Because to me, as long as you use the gradient not from the time step 0, there is some leakage of the information from the future to the present. And maybe theoretically it's no problem, but conceptually this is a problem. And also it's not what you claim. What you claim is every neural network is kernel machine. But it's like anything that can be trained by gradient flow is equivalent to kernel machine.
So I think it's still different with the previous kernel machine because it depends on the training data you used. For different training data, the model trained to get a different kernel. So that's why neural network is better than a fixed kernel function, because it learns the function, kernel function from the data.
Maybe we can discuss later.
Okay.
Okay, so one more question. Yeah, please.
So in learning theory, there is some gap between the statistical complexity of feature learning regime and kernel regime, such as for single index models or teacher setting. And which regime do you think LPK belongs?
Oh, so you mean the regime of NTK and the mean field, right?
Yeah.
So it does not belong to NTK regime or mean field regime, because in NTK and the mean field, you always require the ultra-wide neural network. But here we don't require the width of the network, and we only require the gradient flow training. So very small learning rate.
And In terms of sample complexity, so
oh, sample complexity.
Yeah. So here's the sample complexity actually. So to be honest, the current bound is not tight enough. So we are trying to improve the bound to get a better bound, and we expect to. So we expect the bound is 1 over square root n. So it's similar to the classical regime, but the bound will be tighter because the factor it depends on can be much smaller. Thank you.
Okay, maybe we can move the discussion to offline, and let's welcome Professor Li Qingzhang give a close remark.